Welcome to a pre-recording of the SDN Summit 2013 presentation on multi-vendor SDN, given by TALEF's Chief Technology Officer, Håkan Millroth.
Okay, so I will talk about multi-vendor SDN, and I will describe 6 design principles for doing SDN in a multi-vendor environment. And I would like to start with a quote from one of our SDN customers. And this is Deutsche Telekom, the Terastream project. That's probably one of the most ambitious SDN projects in the world right now. This is Axel Klauberg. He is running the Terastream project within DT, and he is also a board member of the Open Networking Foundation. And it's interesting to see what he says about SDN, his view of SDN. What he says is that the reason for us doing SDN is that we can program services instead of re-architecting the network and the OSS for every new service. We are not necessarily interested in programming the network, but programming the network services is key for us. This concept drastically reduces our time to market from years to weeks. That's the Terastream view of what the business value of SDN is. So the interesting takeaways here, for me at least, is first of all the focus on network services. And secondly, the fact that Terastream has a heterogeneous multi-vendor network with both traditional hardware networking devices and cloud-based software appliances. So it's an interesting combination of technologies in the network layer. And on top of that, there is an SDN solution deployed. Okay, so if we look at SDN as a black box, what's below it and what's above it? So obviously in the lowest layer here in this system stack, we have a network where we have conventional hardware-based switches, routers, other traditional hardware-based network elements. Increasingly, we have virtual appliances, that is network functions delivered as software applications running on virtual machines. And we're also starting to see OpenFlow switches and OpenFlow controllers with applications built on top of them. Okay, so that's what's below this SDN black box. If we look at what is on top of it, it's various kinds of management applications. There are policy engines. In a provider environment, there is OSS, BSS systems, cloud orchestration systems, workflow engines. What we always see nowadays is also some kind of self-service portals for enterprise customers. And also an important management application is user interfaces for network engineers, because network engineers need to be able to troubleshoot and debug and have transparency into an SDN system. It cannot be completely a black box. So these management applications, policy engines, etc., they read information from the network and they write information, state information down to the network. And that's the task of the SDN system. A simple definition of services in this context is anything with an SLA. If you have a service level agreement, then it's a service. So there are typical examples are layer 2 VPNs, layer 3 VPNs, virtual networks, of course, virtual data centers. Well, basically anything that can have an SLA is a service. So the task of this black box or blue box in the middle here, the SDN system, is implementing those network services. Because traditionally in a non-SDN system, if you ask yourself, where is, for example, my VPN implemented? The answer is that VPN, you cannot point to a software application saying, this is my VPN implementation. The implementation of it is distributed across many devices in the network. And a key concept of SDN is that the service implementation is centralized, at least from a logical point of view. It's a centralized implementation of network services with a centralized API. And when I say logically centralized, I mean that from a programmer's point of view and from a user's point of view, it's centralized. It might be a clustered architecture for scalability reasons, but the APIs and the user interfaces give a single system view of it as a logically centralized system. Okay, so that gives us design principle number 1. An SDN system is a logically centralized implementation of network services. Another key idea of SDN is that we have some kind of central repository or central database where we have data structures representing the network services and the network resources and their state. And that is very different from traditional networking, where we have a completely distributed state in the network. Here we have sequential data structures that we can program with, graphs and trees, rather than distributed state in the network. And that simplifies programming the services and programming the network immensely, because then we are back in the familiar realm of sequential programming, basically. Okay, so that's design principle number 2. Data structures representing service state and network state. Okay, once we have that logically centralized implementation of the services and the data structures representing their state, what we need is a semantically rich way of describing this data, this network config state. So we need data models describing those data structures. So data models in this context are semantic descriptions of network resources and network services. And they form an enforceable contract between the SDN system and the management applications, and between the SDN system and the network. And with enforceable here, I mean that typically the data models contain integrity constraints and policies and things that can be verified at runtime to be true. Otherwise the system won't accept it. Once we have data models describing our services and our network resources and their state, what can we do with those data models? Turns out we can do quite a lot, actually. We can auto-render a lot of interfaces from those data models. So we can automatically render the northbound APIs to the management applications. We can auto-render the user interfaces, the GUIs and the sort of network command line interfaces. We can auto-render the internal database schemas used within the SDN system. And finally, we can also auto-render the southbound communication or command sequences that we push out, deploy to the distributed network from those data models. And this is important for 2 reasons. One is that it's always better to have software generating interfaces than program interfaces by hand. But secondly, and more importantly, if we have one set of common data models and auto-render all these interfaces, we are guaranteed that they're always consistent with each other. So we don't get feature drift between the interfaces. The data model is the answer, and then we sort of render everything from those data models. So that's design principle number 3. Data models for services and data models for network resources. So now we have a framework for SDN here, really. We have a logically centralized implementation, we have data structures instead of distributed state, we have data models describing those data structures. Now we have a framework for implementing network services. When we talk about implementing network services, here we mean things like create a service, update a service, delete or decommission a service. And a typical example here would be a layer 3 VPN. So say you need to add a leg to a VPN. You need to add a branch office. That is a simple operation on the service layer. It's just sort of an update service operation. But it results typically in massive state changes in the network. You probably, in many cases, you might do significant reconfiguration of dozens of provider edge and customer edge routers to do that. So there is a huge gap in abstraction level between those service operations and the actual state changes in the network. So how do we bridge that gap, that sort of semantic gap? That's sort of the answer to that is the key to implement services in an SDN system. And the way to do that is well, we need obviously to map these high-level operations on services to state changes, and we do that in 2 steps. We do the first reasonably straightforward step now, since we have a centralized database or repository of data structures. We can do a data structure to data structure mapping. So we can map service data structures or service state as a data structure to network state as a data structure as step 1. Okay? And then as a next step, we need to map those data structures describing network state to device-specific command sequences for whatever devices we have in the network and deploy that in the network. And that can be CLI commands, it can be netconf operations, it can be OpenFlow commands, it can, whatever the network, the interface is exposed by the devices in the network is what we need to use here. So this is a 2-step way of bridging the high level of service operations and the low level state changes in the network. Okay, so that's design principle number 4, mapping service operations to network state changes. Okay, going back to that picture. So this mapping is quite complex, obviously, because it's a lot of things involved. But since the network layer here is a distributed system, it's actually a much more complex problem than I have hinted at here. And the complexity is error recovery. Because in every time you do updates of a distributed system, the thing that is really, really complex is error recovery. How do you ensure that you have consistency when there occurs errors when you have a distributed system? A good way to do that is actually using a true and tested technique for solving this problem, which is transactions. Coming from the database and distributed systems world, that's what we use for dealing with error recovery in distributed systems. And that's what we do here as well. So we provide an end-to-end transactional guarantee, all the way from the high-level create, update, to delete service down to the state changes in the network is done as a single atomic transaction, meaning that we have an atomic change set here. And that is, here I often get an objection from technical people. How do you do that when you have devices in the network that don't support transactions? Like, for example, Cisco devices where the only interface is CLI. How do we support distributed transactions for those devices? And at the end of this talk, I'm gonna explain how we do that. It probably takes 5 more minutes, but I'll save that until the end of the presentation. But for other devices that, I mean, there are network devices that have excellent support for transactions already built into them. For example, every device that supports the NetConf protocol has good support for transactions built in. But it's absolutely doable to do with non-transactional CLI devices as well. So this is the key building block to handle error recovery in this mapping sequence. Okay, so then we have design principle number 5, transactional guarantees for the whole change set. So now I've gone through 5 design principles of SDN here, and I haven't mentioned OpenFlow once, I haven't talked about NetConf, so obviously obvious question is, where does those open standards fit into this design model? And the answer is that we need to look at different controller systems. We're assuming here that we have a multi-vendor, multi-technology network. And the OpenFlow controllers, they control the OpenFlow switches in the network. That's their role. And what's called the multi-technology controllers here, they control other devices that have other interfaces than OpenFlow. NetConf, CLI, can even be SNMP, or some other proprietary interfaces. What's important to realize is that this picture is sort of logical controllers. In reality, you have clusters of OpenFlow controllers and you have clusters of multi-technology controllers as well, for scalability reasons, typically, at least in large systems. Okay, and another topic that is sort of important here is, what's the role of open standards? We have talked about OpenFlow, NetConf a little bit here, but what is the role of open standards in SDN in this framework? Well, we talked a lot about data models here. Data models are central to this design. And there is an IETF data modeling standard called YANG. It's an RFC 6020. It's quickly becoming de facto standard for modeling in the networking space, both for service modeling and for modeling devices. And OpenFlow is certainly getting a lot of traction, especially in some application domains in the data center, but also in general for applications like service chaining is where we see a lot of interest actually for OpenFlow for service chaining. Solves a very concrete problem in that domain. NetConf is becoming increasingly provided by the network vendors. They increasingly having NetConf interfaces, but in reality, the vast majority of hardware-based and software-based network appliances out there for the foreseeable future will have non-standardized interfaces. They will have, the only way to program them is through the CLI or through some other proprietary means. So any system that sort of aims to do SDN in a multi-vendor, multi-technology context need to be able to interface to those interfaces as well, to those protocols as well. So that's design principle number 6 here. We need to have multi-protocol support. That's key. So these are 6 design principles for SDN that sort of allows you to do SDN in a much broader area than just focusing on OpenFlow or just focusing on NetConf. I mean, let's focus on the networks we have out there today and see if we can apply some sound SDN principles to those networks and get the benefits out of it. So then, what are the benefits? Well, the quote from Axel Klauberg hinted at that, but I will do a summary of what we see our customers, what they are looking for when they deploy SDN systems. Obviously, faster development and deployment of services is key. That's probably the number 1 driver here. And very related to that is fast turnaround time for adding new features to the services that you have. Another application which has to do with the fact that you now can read state information from the network and act on it in real time, since you have programmability of the services and the network, is that you can do more dynamic capacity allocation in your network. It's an important application. And since this network, we are sort of leaving the old paradigm of network engineers logging into individual devices, reconfiguring them, looking at an Excel sheet of what to do, but rather have a software-driven model. We obviously get fewer human errors and therefore better quality in our network. So that's the benefits that customers are looking for when they deploy SDN systems. I promised to go back to this question about how do we actually do error recovery in a distributed system with CLI devices. How can we provide transactional guarantees for doing that? The reason why that is a hard problem really is what we need to do is automatically changes to devices, and we don't know which state those devices are in when we need to do the rollback if we have an error. That's the key of the problem here. So we need some tools to solve that problem. What we do need is a CLI engine that we can run in both what we call forward mode and also in reverse mode. So this describes a CLI engine running in forward mode or normal mode. And this is actually a description of how any CLI or most CLI implementations on a switch or router or any device works. The input is a sequence of CLI commands. The red graph here is a data structure representing the config state. And then we have a data model that describes how the CLI command sequence changes that graph or any graph. Right? So those are the three inputs here to the CLI engine. Sequence of CLI commands, a graph representing config state, and sort of the guiding principles, how do the CLI commands transform a graph to another graph. And the output here is a new graph where we have run the sequence of CLI commands and got to a new config state. That's sort of running a CLI engine in a traditional forward mode. But we also need to be able to do automatic error recovery is running such a CLI engine in reverse mode. And that's more interesting actually, because what we then have is the red graph here is the sort of before state, and the blue graph is the after state. And what we are looking for here is what sequence of CLI commands will transform this red graph into the blue graph. And that's running the CLI engine in reverse mode. So if we have these two tools, a CLI engine in forward mode and a CLI engine in reverse mode, then we can actually do automatic recovery of CLI devices. So I'll describe briefly how that is done. So the algorithm for doing automatic error recovery on a CLI device as part of a transaction is the following. It's two steps. The first step is running the CLI engine in forward mode. And the command sequence here is basically a CLI command dump at the time of the error. So we do something like show running config, get a CLI dump at the time of the error. We don't have any initial state, it's an empty initial state. And the CLI engine then constructs a data structure representing the state when the error occurred. So now we got some new interesting information here. We have a data structure representing the state when the error occurred. And when we have that, we can run the CLI engine in reverse mode. So the blue graph here is the state when the error occurred. The orange graph here, or brown graph, represent the state just before the transaction started. And if we run the CLI engine in reverse mode, what it will give us output is the sequence of CLI commands to get from the blue graph to the orange graph. That means it will restore the device to its initial state before the transaction. So that solves the error recovery problem automatically for CLI devices that don't have any built-in support for transactions. So that's how it's done.